So these three-dimensional problems are not difficult. You have first a right-angled triangle, and then you have a non-right-angled triangle. In the right-angled triangle, we use the definitions, the very definitions I'm talking about. Opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. But in a non-right-angled triangle, we often, most of the time, use the sine rule. When do we use the cosine rule? Two conditions. If you have two sides and an included angle. But also if you have squares and or square roots, then you know that I must use the cosine rule. Similarly with the area rule. If this is 3 centimeter and this is 4 centimeter, you don't even need this angle here, because the area here would be half base times height, which is half 3 centimeter times 4 centimeter, which is 6 centimeter squared. However, suppose this PQR is not right angled, then we use the area rule, which can also apply here, that says area is equal to half the product of the two sides times the sine. The sine of what? The sine of the included angle. And again, another thing, the easy thing to remember is that the so-called included angle is very simple. It is the angle made up by the very sides we are talking about. This PQR, which in this case happens to be 90, is the included angle between 3 centimeter and 4 centimeter, because one arm of this angle is PQ, the other one is QR. So it will be the sine of 90. Now, you have half times 3 times 4 is 12 centimeter squared times 1, because the sine of 90 degrees is 1. You still have your 6 centimeter squared. It is unnecessary to use this one when the triangle is right angled. But suppose this was 60, then you don't have a choice, because you can't use half base times height. Perpendicular height necessarily means that this and that must be perpendicular to each other. In other words, it means that PQ must be perpendicular to QR in order for you to use the area rule, or rather the area of a triangle in the form half base times height. So normally when you have a right angled triangle, there's no problem with finding the sine. There's no problem with finding the cos. There's no problem with finding the tan. There is also no problem with finding the area. It is when the triangle is not right angled that we resort to our knowledge of the rules, the sine rule, the cosine rule, and the area rule. Let us look at the rules. I did not derive them because the assumption is if we are doing this section, they must have been treated already. If you have not treated them, I will not derive them, but I will simply write them down and explain what it's all about. Let's start with the sine rule. In any triangle, consider triangle ABC. Any triangle. Let's make it acute. You can put A anywhere, B anywhere, and C anywhere. The convention in mathematics is to choose the side opposite the angle to have a small letter, the same as that of the angle at the vertex. So this would be A, this would be C, and this would be B. Now obviously you cannot say opposite over hypotenuse. For instance, to start with, hypotenuse is strictly that side which is opposite a right angle. So if the right angle is not there, you cannot use the sine definition. But what does the sine rule say? It says choose any angle. Let's choose A. Determine its sine. Put it over the side opposite that angle. It is equal to, in the triangle, the sine of any angle that you prefer to choose divided by the side opposite it. And finally we can have this. This is the sine rule. But the beauty of it is that at any given time we use any two of them. We use this one, or we use this one, or we use that one. But what do you notice? You have 1, 2, 3, 4 variables. So 2 angles, 2 sides. In order to solve using the sine rule, you must have 2 of the same kind and 1 of the other. If you have 2 angles, let's suppose you are looking for B. You'll have 2 angles, and the side that is given must be opposite one of the angles. Let's suppose it's A that you don't know. The 2 sides A and B are given, and the angle B is given. The other angle that the other angle that is, or other side, there is the side that is given, or rather the angle, because we have 2 sides and an angle. The angle, this angle here, must be opposite one of the given sides. So with the sine, we use 2 of an angle, 2 sides, and 2 angles and side opposite. Let's call this angle 1, angle 2. Either angle 1 or angle 2. Similarly, if it is 2 sides, we have either side 1, side 2, and an angle must be opposite either side 1 or side 2. It has just been indicated that I have only 5 minutes. So it's less than that. Now, that is what the sine rule is said. So you must be having 2 sides and a side, 2 angles and a side opposite one of the angles, or 2 sides and an angle opposite one of the. Then you can use the sine rule. What about the cosine? I'll use the same triangle. I'll use the same triangle. They say choose any side. Let's choose B. Take its square. It is equal to the sum. After taking B, you are left with A and C. It is equal to the sum of this. Does this look familiar to you? Yes, the theorem of Pythagoras. Only 1, this triangle is not right angled. 2, we are not done. Minus twice these 2 sides, but not squared this time, the product of these 2 sides, times the cosine of the included angle. Now, like I said, the included angle is nothing except the angle made up by the very sides A, B, B, C, which is C and A. So it is the cosine of B. Now, this applies to any other side. A squared equals B squared plus C squared minus 2BC, the cos of A. And finally, C squared equals A squared plus B squared minus 2AB times the cos of C. And like I said, you will notice that there's a square here. So if your problem has a square or a square root, that tells you that here I'm called upon to use the cosine rule. This is what we've been applying. I've been applying them without going over them because the assumption is that you have already treated the section. And